Chapter 6, Lesson 1, Part 2 begins on page 165 for your reference, and we're going to jump back to 168 to continue and finalize our reading. On page 165, you can see and look at the energy steps diagram that looks just like this on the top of page 164, 165. Here you've got a model of what the energy clouds look like, or the energy steps look like, in terms of where electrons exist based on the number of electrons that are in an element. Here you've got the nucleus. In this first level surrounding a nucleus, there can be up to 2 electrons. In the next energy level, there can be up to 8 electrons. In the next energy level, you can be up to 18 electrons. And in the last energy level that's represented on this model are 32 electrons. Now you can find out how many electrons would be in the 5th and 6th and 7th energy level by using the equation 2n squared, if you take n as the number of energy levels. But this is a reminder for where these electrons exist. Now this is important to know because the electrons indicate the type of atomic structure and then the type of reactivity that an atom of an element has, because the electrons are kind of what dictates when an atom is satisfied or happy with how many electrons it has in its outermost energy level. Now, if you look at this diagram, this shows where those energy levels are populated. If all of the elements have the same number of arrangements or energy levels, then it's organized in a fashionable way that looks just like this. So for hydrogen, hydrogen only has 1 proton given its atomic number, therefore it has 1 electron, and that's drawn here. Helium has 2 electrons because it has 2 protons. It's got 2 electrons in its first energy level. As you work from left to right then, in these rows, you can see that each number indicates another electron being added, because that number is also the atomic number, a number of protons being added. So lithium has 3 electrons, beryllium 4, boron 5, carbon 6, nitrogen 7, oxygen 8, fluorine 9, and neon 10. As you go across this row, as each electron is added, you notice that after 2 electrons, all of them are added in. As you go down to the next level, elements sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon all have a 3rd energy level, with electrons being added to that 3rd level because the first 2 electrons are in the 1st level, the next 8 electrons are in that level, and then the 11th electron, sodium, is in this 3rd level. The 11th and 12th for magnesium is in this 3rd level, and the pattern continues. As you add more electrons, that 3rd level starts to fill up, and that 3rd level can have up to 18 electrons. You might see here in potassium and calcium that all of those are represented in that next outer energy level until there's a completely full shell in that level of electrons. Now, it's important for us to know this, but this is actually really difficult to use and to communicate among scientists. They have to draw a diagram with all these different dots on it. There's got to be an easier way. Well, that's where electron dot diagrams come into play. I'm reading on page 168, electron dot diagrams at the top of the page. You've read that the number of electrons in the outer energy level of an atom determines many of the chemical properties of the atom. Because these electrons are so important to determine the chemical properties of the atom, it can be helpful to make a model of an atom that shows only the outer electrons in that atom. A model like this can be used to show what happens to these electrons during reactions. So instead of using all of the electrons that are in an element, we want to make a diagram of just the ones in the outermost energy level. So for example, here boron has a total of 5 electrons, but only 3 would show up in an electron dot diagram. Carbon has 6 total electrons, but only 4 would show up in an electron dot diagram. It simplifies it and makes it a lot easier to draw out than having to put all these dots in order to identify all of the electrons that are being used, when it's only actually the ones in the outermost energy level that have an effect on how that atom and that element are going to react. Drawing pictures of the energy levels and electrons in them takes time, especially when a large number of electrons are present. If you want to see how atoms of one element will react, it's handy to have an easier way to represent the atoms and the electrons in their outer energy levels. You can do this with electron dot diagrams. An electron dot diagram is the symbol for the element surrounded by as many dots as there are electrons in the outer energy level. Only the outer energy level electrons are shown because these are what determine how an element can react. Well, how do we write them? How do you know how many dots to make? Well, for groups 1 and 2 and 13 through 18, you can use the periodic table or the portion of it shown in figure 5. Group 1 has 1 outer electron, Group 2 has 2, Group 13 has 3, Group 14 has 4, Group 15 has 5, Group 16 has 6, Group 17 has 7, Group 18 has 8, and so on. All members of Group 18 have stable outer energy levels from neon down. They have 8 electrons. Helium has only 2 electrons because that is all that its single energy level can hold. The dots are written in pairs on 4 sides of the element symbol, starting by writing 1 dot on the top of the element symbol, then work your way around, adding dots to the right, bottom, and left. Add a 5th dot to the top to make a pair. Continue in this manner until you reach 8 dots to complete that level. Here's an example of what those Lewis dot diagrams look like. So for hydrogen, you draw 1 here. Helium, you're starting on the right, now has 2. You draw the second one on top. Now for hydrogen is in this element family here, the alkali metals, and helium being in the noble gases. On this side, helium is the only one that doesn't consider itself part of the noble gases, but it's organized in that way on the periodic table. Go back over here to lithium, you can see how this sequence works. Lithium has 3 total electrons, 2 are in the first energy level, the last one in the outer energy level is drawn right here. Then as you go right on this period, beryllium has 2 inside and 2 on the outer energy level, so the first one's drawn here, the second one's drawn here. Boron has the first one drawn here, second here, third here, carbon 1, 2, 3, 4. And now if you get to nitrogen, you'd continue in that pattern, 1, 2, 3, 4, and then you draw another one where you have an overlap of those items. That's shown at the bottom of page 168. Now, here's what your homework assignment looks like, and maybe this video is going to help as we continue learning how to write these items out. Here's what that answer key looks like in terms of how you would draw those. So for nitrogen, you'd have 1, 2, 3, 4, 5. Oxygen, 1, 2, 3, 4, 5, 6. As you work your way around the electrons, you're drawing one at a time in each of those spots, and then as soon as you get to more than that, you're going to draw in that second portion or that second dot, equating to however many are there to indicate that you're getting to and working to having a full set of electrons and that outermost energy level. The dots are written in pairs on 4 sides of the element symbol. Start by writing 1 dot on the top of the element symbol, then work your way around, adding dots to the right, bottom, and left. So in this example, it starts it on the right-hand side and draws it around. In your book, it tells you to start on the top and work your way around. Either way is correct. You can write it in one of those positions, and then the next one goes in the next position in a counter or clockwise way, as long as you understand that as you're drawing 1, 2, 3, and 4, they're in 4 different spots. Carbon's the best kind of example of that. The process can be demonstrated by writing the electron dot diagram for the element nitrogen. First, write N, the symbol for the nitrogen, then find nitrogen in the periodic table to see what group it's in. It's in group 15. If it's in group 15, you know that it has 5 electrons. So you have to draw 1 on each side, and then the 5th electron is in a double up fashion. So that is shown right here. Oxygen is in group 16, so it has 6 electrons in its outer energy level. Therefore, you're going to draw 1, 2, 3, 4, and then 2 of those double up. Fluorine is in group 17, which 17 means it's got 7 electrons in its outermost energy level. 1, 2, 3, 4, 5, 6, 7. Neon is in group 18, and it has 8 electrons in its outermost energy level. Now, why would we ever need to use this, or why would scientists use this information? Using dot diagrams on page 169. Now that you know how to write electron dot diagrams for elements, you can use them to show how elements bond with each other. A chemical bond is the force that holds 2 atoms together. A chemical bond unites atoms in compounds, much as glue unites the pieces of the model in figure 10. Atoms bond with other atoms in a way that each atom becomes more stable. That is, their outer energy levels will resemble those of noble gases. So we draw these electron dot diagrams to show how many electrons are in this outermost energy level of that atom, and then we see, well, what does it actually need to feel stable? What does it need to feel like it's completely comfortable? Neon has a full outer energy level, so it doesn't need anything else. But fluorine has 1 missing. It needs 1. Lithium has 1 to give. Maybe those two can combine because there's 1 to give, 1 to get rid of, and there's 1 that it's needed. So you'll see that our alkali metals and our noble gases will often have that reaction, such as in the case of sodium and chlorine. Chlorine needs 1 electron to have 8. Sodium needs to get rid of 1 so that its first energy level has 2. It will dump those over here and be able to make that connection to sodium chloride as an example. Now, Mr. Chain's going to go through the 2 parts of the assignment that he has assigned for you. That's the energy level page that looks like this, how we'd actually write out where those electrons belong, and then your homework assignment that looks like this, or we're going to fill in and practice writing those Lewis dot diagrams. We'll demonstrate that using my dot cam. You can follow along and complete that activity with us. Thanks for following along. To complete our homework for today, we first have to go back and understand that we know how to think about and populate the number of electrons that are in each of the elements that are presented here for us. We're just going to look at elements numbers 1 through 20. We want to know how to identify how many electrons are in an element and then identify where those electrons are based on the electron cloud theory, where those items show up, the different energy levels. So what Mr. Shane has in front of him is his periodic table, because the periodic table has the numbers on top of each of these columns or element families that's going to indicate how many electrons in the outermost energy level. It also gives me the atomic number that tells me how many protons are in an element, and that indicates the number of electrons if we're assuming that these are neutral atoms. Then we're just going to be able to fill in each energy level based on how many electrons we know fit into each energy level. You can see that a couple of these on your homework assignment are done already. We're going to work through completing the rest of those. Hydrogen has the atomic number 1, it has 1 electron. Helium has the atomic number 2, it's got 2 electrons. Now that first energy level is full. As we jump down to this next level, lithium has a total of 3 protons, therefore 3 electrons. There are 2 in this first energy level, and the third is in that next outer energy level. Let's continue with this pattern as we go across this column. Number 4, beryllium, obviously has 4 protons because of the indicated 4 as the overall number. Mr. Shane's got to get his pen to work. There it is. You've got 2 electrons in the first energy level, and then 4 gives us a total of 4, so there's going to be 2 electrons, 1, 2 in the next energy level. 5, there's always 2 in that first level. 5, boron has 5 protons and 5 electrons, so 1, 2, 3, 4, 5. Carbon has 6, so if we've got 2 electrons in the inner level, a total of 6 would be plus 4 more. 1, 2, 3, 4, and you'll notice when I'm putting in the electrons, I want to actually try to evenly space them out because electrons actually have the same charge as each other. They're both negative. They don't want to actually be by each other, so they want to spread out in that space that they have in that electron cloud and being how that's represented. Nitrogen has a total of 7 protons, therefore 7 electrons. Let's count them up. 1, 2 in the first energy level, 3, 4, 5, 6, 7 total. Oxygen has 8. 2 in the first energy level, 3, 4, 5, 6, 7, 8. 9 for fluorine, 1, 2, 3, 4, 5, 6, 7, 8, 9. And neon is done, taken care of right here for us. Now, another way in which we can check if we got this right is if we have our periodic table here in front of us. In group 13, boron has 3 in its outer energy level, and carbon has 4, nitrogen has 5, oxygen has 6, fluorine has 7. If I go back and look at how many electrons are in the outer energy level here, beryllium had 4, boron had 3, carbon has 4, nitrogen has 1, 2, 3, 4, 5, 6, 7, and 8. So the indicator from the total number of electrons says just fill this out based on those energy steps. The next way to check is to make sure that the number on the column or the element family head here tells us how many are in that outermost energy level. I like to use both strategies to make sure that I have a complete understanding of where those electrons go. Let's take a look at magnesium. Magnesium has a total of 12, so I can use the first strategy, count up where those go. 2 in the first level, 8 in the next level, and then however many left over in the third level. Or I find magnesium on my periodic table. Magnesium in the periodic table is in this second column, meaning that it's got 2 electrons in its outermost energy level. Let's just make sure that that's how that plays out. There are 2 in the innermost level, 1, 2, count the total, 3, 4, 5, 6, 7, 8. Now how many can go in the second level? I think it's a total of 8. 1, 2, 3, 4, 5, 6, 7, and 8. Now the total now is 10. 2 plus 8 is 10, and there needs to be 12, so there's 2 more. 1, 2. We just predicted, based on where it was in the periodic table, that it would have 2 electrons in the outermost energy level, and it does, with the total being represented in each of the other levels. Aluminum has a total of 13, so my first level has 2. My next level has 8. 1, 2, 3, 4, 5, 6, 7, 8. That's 10, and then there would be 3 more in this outer level because it has that 3 in it in terms of where it's located on the periodic table. Aluminum is in group 13. It has 3 in the outer level. Silicon has 14 total. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That means 1, 2, 3, 4, 5, 6, 7, 8 are in that second level. 2 are in the first level. 4 are going to be in that outer level. 1, 2, 3, 4, because silicon, again, is in column 14 right here. You can probably bet that this follows a pattern, as in phosphorus is in column 15, sulfur is in column 16, chlorine is in column 17, calcium is in, or argon is in group 18, in this last column that has that number of electrons in the outermost shell. So I'll just continue. Phosphorus has 15, so this is 1, 2, I'm going to count to 10, 3, 4, 5, 6, 7, 8, 9, 10. 15 means there's 1, 2, 3, 4, 5 in that portion. Sulfur has 16, so there's 2 in the innermost, 8 in the second one, 2, 3, 4, 5, 6, 7, 8, 9, 10. Total of 10, and there's 6 left over. 1, 2, 3, 4, 5, 6. Chlorine has 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 8 in that second level. Now there's 17 total, so I have 7 left over. 1, 2, 3, 4, 5, 6, 7 in that outermost energy level. The last one that we have here is calcium. Calcium has a total of 20. I can think 20 and then add them up, 2 in the first, 8 in the next, 18 in the third energy level. Or I can think and look at my periodic table. Calcium finds itself in group 2, which is going to indicate that it has 2 electrons in its outermost energy level. So we have a number of energy levels that are represented here. We can put the right number of electrons in that outer level. Calcium has 2 in the first level. It has 8 in the next level. 1, 2, 3, 4, 5, 6, 7, 8, giving it a total of 10 so far. Then in the next level I can have 8 as well. If you look at potassium here, it's got 2, then 8 is 10, and then it has 1, 2, 3, 4, 5, 6, 7, 8, and then the ninth one is outside of that. So I can have 8 in this third level. 1, 2, 3, 4, 5, 6, 7, 8, and now I have 2 way on the outside for calcium. All right? Now, potassium has 1 because it's in group 1. Calcium has 2 because it's in column 2 as that outermost energy level. Now, what that does for us is helps us understand where those electrons are, and by identifying what's in the outermost energy level, we can then predict how those elements are going to react and or form bonds. But this is really complex. I don't know if you noticed that we're just drawing a million little dots on all of these different elements, or these electron clouds for those elements, and it's really tedious. This isn't what scientists actually use. So we're going to take this knowledge and turn it into the way in which scientists actually communicate with one another, and that's this part of the assignment. Here's where we're going to take what we learned here and transfer it onto this piece of paper. Here, some of these again are done for us, and they're probably going to match up. Hydrogen has 1 electron because it's got 1 electron in its outer energy level. Helium has 2 electrons drawn here because it has 2 electrons in its outer energy level. Remember, the Lewis dot structures or Lewis dot diagrams only show the electrons that are in the outermost energy level. So if you keep this on hand, you keep track of how many are in that outer level, you can actually fill in this relatively easily. Lithium has a total of 3. There's 1 in the outer level. Beryllium has a total of 4. There's 2 in the outer level. Boron had 5. There were 2 in the outer level. Carbon had 6. There's 4 in the outer level. Nitrogen then, if I look at this piece of paper, has 1, 2, 3, 4, 5 in its outer level. How would I go about writing those? In your book, it says write a dot on the top, the side, the bottom, the side, and then as soon as you get to 4 and then 1 more, this one has 5, you would double those up. Okay? Or, as it's described in another way, you can start on the left-hand side and then work your way around and have 1 on all 4 sides, and then oxygen has a total of 8, so there's 6 in the outer energy level. You double them up in 2 different spots. There's not really a wrong way to do that because you're communicating how many electrons are in those outer energy levels. So fluorine has a total of 7. I'm going to draw 7 dots in that same fashion, working from one side to the next, to the next, to the next. 4, 5, 6, 7. Neon's going to have 8, which means it's got 2 on each side, so it doubles up all the way around. Sodium, back over here in the left-hand column, looks like it has a total of 11 electrons. So I draw 11 dots? Well, no, I only draw the number of dots that are in the outermost energy level. So there were 2 in the first level, 8 in the next level, and then there's 1 alone way on the outside. I can either draw it on the right-hand side here or on the top. I'd accept either answer. Magnesium then has 1. In this column, you're going to have 2. You might draw it like this. As you go, you're going to see this pattern start to develop. If 2 was here, then boron had 3. I bet you there's going to be 3 here, and they're going to look exactly the same. 1, 2, 3. Silicon is with carbon in that same element family. They have 4 electrons in their outermost energy level. Phosphorus has 5, just like nitrogen. 1, 2, 3, 4, 5. Sulfur has 1, 2, 3, 4, 5, 6, just like oxygen. Fluorine has 7, so chlorine has 7. 1, 2, 3, 4, 5, 6, 7. Argon is going to be with neon in those noble gas sections, having a total of 8. 1, 2, 3, 4, 5, 6, 7, 8. Now way down here at potassium, here you've got the atomic number 19, meaning it has 19 protons, 19 electrons. Are we going to have to draw all those dots? Well, the answer is no. There's only 1 electron in the outermost energy level. Therefore, I only need to draw 1 dot. Calcium has 20 total electrons, but I only need to draw 2 because there's only 2 in those outermost energy dots. Hopefully you can see that that pattern starts to develop as this family has the same number of electrons in the outermost energy level, same number of electrons in the outermost energy level, same number of electrons in the outermost energy level, and that's going to indicate what those elements and those element families are going to do on a regular basis in terms of what they are reacting with. The atomic structure is directly related to how those elements behave, or the elements where those electrons are organized in those elements directly relates to how those elements are going to behave. Thanks for following. Thanks for completing that activity with me today. God's blessings.